Hi everybody, thanks for tuning in. Today I'm going to be talking about digital logic circuitry, specifically combinational logic circuits. There's another type of circuit called sequential logic circuit. The difference is combinational logic circuits cannot possess memory, whereas sequential logic circuits do indeed possess memory and are the functional components of memory elements in your computer. I'll do another video on that after this one. To understand stuff about digital logic circuits, we need to understand what Boolean algebra is. You may or may not have heard of this in the past. If you haven't, Boolean means true or false. This is similar to the way that computers reason using the binary language. Binary is actually a number system. And what we're going to be doing is representing true as 1 and false as 0. This is how computers actually read data. It's just all a series of 1s and 0s. So what is Boolean algebra? Boolean algebra is the theoretical underpinning of logic circuit design. It consists of our true and false and a few logical operators, which we're going to dive into now. The first operator is called AND. To represent what AND means, we're going to draw something called a truth table. But first, let me draw a simple circuit. Let's take two inputs, x and y, into this logic gate, and this is an AND gate. Our product looks like this. X and y, or also this multiplication dot. Now, to understand what this means, let's list out a series of values and outputs, inputs and outputs. Now, when drawing these tables, what you want to do is essentially count up in binary, and it's easy with just 2 bits. What we have is 0 and 0, which is 0 in binary, 0 and 1, which is 1 in binary, 1 and 0, which is 2 in binary, 1 and 1, which is 3 in binary. Now, to just explain this if you don't know how to convert binary to decimal, let's look at the number 7 in binary. 7 is represented by 3 bits. To understand how binary works, is we look at the 2 to the 0 place, 2 to the first, and 2 to the second place. These numbers are 4, 2, 1. To get 7, we simply add all of the places where there are 1 together. If we look at this number, we can see that we only add the 4 and the 1 and get the number 5. And so that's how counting in binary works. Now let's look at the actual logic implemented by the AND gate. 0 and 0 is going to be 0. 0 and 1 is also going to be 0, which means that 1 and 0 is also 0. 1 and 1, on the other hand, is 1, because what AND is actually telling us is when both and only both inputs are true, will the output be true. This can also be read as false and false is false, false and true is false, and so forth. Only true and true yields true. Now let's look at the OR gate, or the OR operator. Again, we're going to have 2 inputs and call them x and y. The OR gate is drawn like this, and its output can be represented with the plus sign, x or y. Let's draw a truth table. Now we can see we've listed out the same binary combinations again. These are actually all of the different combinations that can be represented with only 2 bits. So, how does OR work? Well, let's work it out. 0 or 0 is 0. Either 1 is 0, so it's 0. In this case, both are 0, it's 0. 0 or 1, you guessed it, is going to be 1. The truth takes precedence in this case. true or false is true, and true or true is also true. The not gate, or the not operator, you'll see written usually this way or this way. And all it means is a negation of what the original value was. Take, for example, if x is 0, x naught will be 1. X naught naught will be its original. Because in Boolean algebra, these negations cancel, and we get the original value back. Now that we've looked at some of the basics of Boolean algebra and binary logic, let's take it and extrapolate that into actual circuitry. Let's just take a truth table with just x and y, and let's call our output f of xy. This is our Boolean function that will represent what the circuit actually does. Let's take the same combination. And let's just say my output looks like that. What I'm going to do is give something called a sum of products form. And what that means is that everywhere my function produces a 1, or a truth, I'm going to take the corresponding inputs and give them as truths, as full truths. And what that means is, because x is false and y is false, I have x and y both negated. That's x naught and y naught, and then sum them with this value, which is x because it's true, and y not. This is the sum of products form. So how is this really relevant to us? Well, we've just said that and or are fundamental operators in Boolean algebra, and that we can draw gates for them as well as for the nots. So that means that we can produce a circuit that does this function. Let's take x and y. We pass that into our AND gate. But we can see that both of them are negated. To represent that in the circuit, we're just going to draw these dots here. That means that they're negated. Now, I'm going to do something here. All I'm doing is drawing an extension down from x and y into another AND gate. Because we can see up here, we have another AND. We have two AND gates. And this time only the y is negated. And finally, we have this OR gate, which means both of these outputs will be inputs to an OR gate. And we get our function. This is a basic logic circuit. So what does this really even matter? Well, we are talking about combinational logic circuits, and some of the most common combinational logic circuits are things called adders. And there's a half adder and a full adder. Let's look at the half adder first. This is actually how computers add numbers. I'll draw the circuit first. Let's take two inputs, A and B. What I'm going to do is pass them into another type of gate called XOR. This is exclusive OR. And we'll look at the logic table. We'll look at the logic and the truth table for this in just a second. I'm going to take B and A again and extend them down and pass them into an AND gate. Now what I have here is a sum. And we'll see what that means in just a second on the truth table. And out here comes a carry bit. We'll also see what this means when we do some binary addition by hand. The sum is actually equal to A naught and B, or A and B naught. The shortened version of this is simply exclusive OR. Our carry bit is equal to A and B. Now let's look at a truth table and see what's actually happening here. Let's take our same combination of two bits. Logically, what we produce with XOR is the following. And that means that exclusively one of them is true, and only that will be true. The carry bit is just an AND, which we saw earlier. Now let's look at an actual practical example of this. I want to take two numbers in binary, the number 3 and the number 2, and I want to add them together. The way binary addition works is 1 and 0 will give us a 1. However, when we add 1 and 1, we get a 0, as we can see here in our truth table. But we receive a carry bit, because we have an extra 1 now that comes up here, and thus we represent this number. 3 plus 2 is 5. And you can check this in binary. That is the fundamental logic of this half adder, and this is how computers actually add numbers. But this is a half adder, right? So there must be something called a full adder to completely add the number. A full adder circuit is essentially two half adders put together. We're going to take our same two inputs, A and B, and we're going to pass them back into our exclusive OR gate. But we have another input here. That's the carry in bit. Now, we'll talk about this when we finish up drawing the circuit and get to the truth table. This is what the full adder circuit looks like. Let's try to break this down a little bit, because it does look a little bit convoluted if you're just taking a glance at it. We saw in the half adder that our inputs, A and B, go into an exclusive OR gate first, and return a sum. But this time we have another input, called the carry in. So, because we're putting two half adders together, we're going to pass these inputs into another exclusive OR gate. These inputs are the product of A XOR B and the carry in. This will finally give us our sum. The carry in is also passed to an AND gate. And the output here, A exclusive OR B, is also passed to this AND gate, which says A XOR B and C in. That's what this is doing. Down here, we just have A and B. So, our carry out is determined by A XOR B and carry in, or A and B. Now let's look at a truth table and do an example so we can see how computers can actually take two full numbers and add them. Take a look at our inputs. Something's changed here. Because we have 3 inputs, we actually have more combinations of bits. This is actually counting up a 3-bit number. 3 bits can represent 7 as the highest number. So we've counted from 0 to 7. That would make sense if you think that 2 to the 3 is 8, which is the number of combinations we have here. An easy way to remember this 3-bit combination sequence is the first column will be 4 zeros, then 4 ones, then the second column will be alternating 2 zeros, 2 ones, and the third column will be alternating to single zeros and single ones. It's a nice pattern to remember binary counting. Now let's take a look at what we get for our sum. we have three inputs, A, B, and our carry-in bit. All of them added together just gives us a sum of 0. Here, we have A and B and the carry-in, which gives us 1. Same thing for A, B, 0 for carry-in. But something changes here when we get two 1s. We saw that the sum of these is 0, and that the carry is 1. That is our carry-out bit. For these, we had no carry-out bits, because there was nothing to carry. But this time, we've overflowed, and we need to carry over a bit to the next order of position in the number. The same follows for the rest of these. Anytime we try to add two 1s in a binary number, we're going to get a carry bit. So let's take the numbers 7 and 5. We know what we should get from this is 12, but we've already said that 12 is too large of a number to be represented by 3 bits. So let's see what happens. 1 and 1, as we've seen, gives us a sum of 0 and a carry of 1. Now we have a carry and 1 and 0, which gives us a sum of 0 and a carry of 1. But now we have 3 1s. We can see here on our truth table, if we have 3 1s for our inputs, we get a sum of 1 and a carry of 1, which gives us our binary number. To check this, consider the powers that we get when we calculate the order of the position in the number. What we would do is add 8 plus 4, because those are the only positions that have 1s. And of course 8 plus 4 is 12. So we've got our number. Let's go back to our full adder circuit, and let's put that combinational logic block into a box, and just imagine that this is a black box that implements the full adder logic that we've already seen. Now, you may have been wondering when we drew this combinational circuit, why is there an initial carry in? But if you were to study a little bit about the 2's complement binary system, you would see the way that negative numbers are implemented using binary bits. There's another important reason for this carry in being part of the full adder input. All we can do now is add 2 bits, but we've seen that big numbers can have a lot of bits, and of course we know that computers can add numbers that are very, very large. The extra importance of having this carry in bit is in implementing something called a ripple carry adder. And this is how adders work in an actual arithmetic logic unit in your PC. We have 2 inputs again, and now let's start distinguishing these. A0 and B0, A1 and B1. And our carry in, you guessed it, comes from the previous carry out. This process continues for up to as many bits as you'd like to add. Usually it's 32 bits or 64 bits that are numbers that are being added by these ripple carry adders. If we look at this in an actual binary addition problem, just to make this a bit more clear, we see that A0 represents the first position in the number, the first bit, and the second, the more relevant one, and so forth. This can go up to 32 bits, which can represent very large numbers. I don't remember the exact number off the top of my head. This can go on for as many bits as you want. Now, in our ripple carry adder, what we have is A0 and B0 being added in this, and our sum is 1, and our carry out is 0. And the same happens here. This is the number 1, and 2, and 3. We'll talk a lot more about these gates and the power that they can produce in the next video, which will cover sequential logic. which is the fundamental underpinning of computer memory. Thanks for tuning in.